So I'm going to use this one problem with 15 parts to summarize our unit so far. So here's the situation. We're going to have our spring. We're going to put our mass, 2 kilogram mass on our spring. We're going to start this at our equilibrium point here. We're going to pull the mass back to some distance. This max distance we'll refer to as the amplitude, or A. We're going to go ahead and let the mass go. The mass is going to start moving this way. It's going to continue. It's going to start to compress the spring and move in this way, and in fact it should move the same exact distance if there's no friction. We can call that negative A, and it's going to continue to go back and forth in simple harmonic motion. So the graph that's going to represent this would be displacement versus time, where this peak right here would essentially be the 0.15, the amplitude, right? It's starting here at 0.15, and then it's going to go through to negative 0.15. This would be our negative A down here. This 0 point would represent our equilibrium. And notice that we have our graph here. If you remember, the equation for this graph looks like this. X equals a cosine of 2 pi times the frequency times our time. 2 pi f times t. And if you recall, 2 pi f is also referred to as the angular frequency, omega. So you could also write it like this. So that's a cosine. You can clearly see it's a cosine curve, right? And it's going to repeat every 2 seconds right here. And then it's going to continue, right, in the cycle. So let's just go through some of these, and we'll stop and kind of review as we go. So actually we already talked about a few of these. So the amplitude, first thing is the amplitude. Well, that would be the max distance that it travels, right? And so we already figured that out. That would be 0.15. We don't got the units here. These are going to be meters. Letter B is our period. Remember, the period is the time for one full cycle. So if we start here, we're going to go down and back. This rep goes down and back. And here took 2 seconds for one cycle, right? Then it's going to repeat itself. So our period T, we should write A equals, period T is equal to, what was it? 2 seconds. 2 seconds. All right, letter C. So our frequency, well, the relationship between frequency and period is simple. It's just 1 over t. So this is going to be a half of a second. And the concept of this, oops, this is not half of a second. This is a half of a cycle per second. So 0.5 cycles per second, or half of a cycle per second. This one you can also write as hertz. That's this normal unit, but I like to use cycles per second. So the concept of this is, well, it takes 2 seconds for one cycle, right? Which means after 1 second, it's only traveled half of the cycle. So that's kind of what frequency means. It's how many cycles, or how many times it does a full revolution back and forth in a second. In this case, since it takes 2 seconds to go back and forth, in 1 second it's only gone halfway. So it's traveled half of a cycle. Letter D is angular frequency. As I mentioned earlier, that's omega. That's simply 2 pi times f. So that's going to be 2 pi times 1/2, just simply pi. And the units for this, if you recall, omega is radians per second. So this one, the concept of this, imagine we modeled this as a circle. So this was our circle going around like this, right? And so if we started over here, and we're traveling this way along our circle, notice that after 1 second we would have traveled half of our circle, which in radians would be pi, right? Half of a circle is simply pi. And in 2 seconds we would travel all the way back here, which would be 2 pi. So one period we travel the full 2 pi, but in this case our omega is just a half a radian every second. So 1 second we travel pi radians. Alright, letter E. What's E say? What is the spring constant? So to find the spring constant, we're just going to use our equation for a period. 2 pi equals, T equals 2 pi square root of m over k. And we'll just go ahead and substitute in what we know. So we know that the period, the time was 2 seconds. This is equal to 2 pi. And then the mass was also 2 kilograms divided by k. We'll do some algebra here, right? Let's square both sides. Square, square, cancel a 2, square the pi. So what's that? We got 1 equals pi squared times 2 over k, or k equals 2 pi squared. Okay, plug that into your calculator. 2 pi squared gives us 19.7. Remember, the units is newtons per meter. That's essentially telling us the stiffness of our spring. It takes 19.7 newtons to move the spring 1 meter. All right, A, B, C, D, E, F. What is the speed at 1 second? So let's go back to our graph here. And at 1 second, here we are, we're going across. Let's look at our spring at the same time. There we go. So we're going across here at 1 second, we're over here. So notice that at this point we just started, we're moving this way, and after 1 second we reach the end, which means we've slowed down and stopped. Now we're going to go back in the opposite direction. Therefore, the speed at 1 second is simply going to be 0, because we've stopped at that peak at the end. Okay, what about the acceleration at the end? Well, at the end, this is going to fully be pushing this way, right? So it's compressed, and at 1 second, we're now going to be pushing back this way. So the spring's going to be pushing with a force Fs. If you remember, Fs is equal to k times x. Actually, it's negative kx to be specific. So we're just going to sum up our forces. In this case, since there's no friction, we just have one force. That's our spring force. We'll set that equal to ma. And as I just mentioned, our spring force Fs is negative kx m times a, or a is equal to negative kx over m. Okay, let's substitute in what we know. So we go negative. Our k we just found was 19.7. At 1 second, we see that our x is going to be negative 0.15. And then we're going to divide by the mass, which was 2 kilograms. Calculator A. So plug it in. I'm going to get an A of 1.48 meters per second squared. Moving along, H. What is our speed at 2.5? So let's look back at our graph. 2.5, notice we're right here. Okay, so we've gone one full cycle, and now we're back through the equilibrium point. So remember, when we pass through that equilibrium point, we've reached our maximum velocity right here. So to figure this out, we're just going to use our conservation of energy. Over here we have our maximum in our spring potential. Over here we have our maximum in our kinetic energy. So we'll use our E initial equals E final. So again, this would be our US max should equal our KE max as we pass through equilibrium. 1/2 kx squared equals 1/2 mv squared. Okay, you could cancel the half if you want. I'm going to leave it just because I know later I'm going to use this US max again. So let's just get the number for that to save us some time. So this is going to be 0.15. This is just at the amplitude, right? The maximum amount. equals 1/2 times 2 kilograms times our v squared. Okay, so when I plug this in, I'm going to get 0.222 joules. So this is the maximum energy of the system, by the way. So once I know this number, I can solve for the energy anywhere because I know it's going to stay constant since there's no friction. 2 cancel, that just equals v squared. Solve for v, square root that, and you get 0.47 meters per second for v. Alright, moving along, hi, find the acceleration at 2.5. So going back here, we're looking for the acceleration at this point. Remember, this is as we pass through our equilibrium point. So when we're right here, the spring is not compressed or extended. Therefore, the force at that point would be 0, and so the acceleration as well would be 0, right at the equilibrium point. So I is easy enough. A is 0. Oops, A is A. A is 0 at equilibrium. Okay, let's look at letter J. Letter J says, what is the displacement at 3.3? So we're going to look at 3.3 here. Now you could estimate with your graph, and I would recommend doing that just to get a ballpark. So at 3.3 seconds, we're looking for our displacement. So it's going to be, what, about right here-ish. So, I don't know, 0.08 is probably my estimate. So, but you are going to have to calculate this out. I do want you to calculate this to get an exact number. So this is where you're just going to use this. We're just looking for x at that specific time, and we're just going to try to find, figure out what it is using that simple equation. So hi, what's that, j? So we'll just use x equals a cosine 2 pi f times t. Okay, so our a is just our amplitude, so that was 0.15. Cosine of 2 pi, frequency was 1/2, and then the time was the 3.3 seconds. Okay, plug it in. Now this is the one time in the whole class where you're going to use radian mode in your calculator. So you're just going to have to remember for almost every other problem, 99% of them, you're going to be using degrees. But this is the one time you're going to want to use radians with your calculator. Make sure you're in radians mode. So yeah, plug it in. Make sure you're in radians, and you're going to get x equals negative 0.088 meters. And my estimate was, what was it, 0.8 I think I said, which is pretty close, okay, or 0.08. It's about 0.09. Alright, letter K, let's find the velocity at 3.3 seconds. JK, let's hold this. So we're looking at the velocity at that time. So we're going to use energy for this. E initial equals E final. Remember, we already know our initial energy. That's just going to be our US max. You could also use KE max as well, but doesn't matter, same number, right? And then at this point, notice that you are that the mass is moving, right? But it's also being compressed. So this would be, since we're in the negative direction, this would be like somewhere over here. And so it's being compressed and it's moving, so it has both spring potential plus kinetic energy. So recall our US max earlier somewhere is 0.22 joules. 0.222 joules. And we'll set that equal to US. So that's 1/2 kx squared, and that's going to be where we are right now, which is 0.088. What was our k? 19 point something? 19.7. 0.088 squared, what we just got, plus our kinetic energy, which is 1/2 mv squared, and our mass is 2, and then our velocity is what we're looking for. Alright, so do the math on this. Let's see if I have it. 0.222 equals, I'll do a little baby step. You get this right here is going to be 0.076. Remember, this is energy. This is energy. So this was our starting energy. We now have this amount of potential, and then this is going to turn into, you know, the difference in kinetic. Okay, solve for V, and I get a V of 0.382. You always want to make sure your answer makes sense. Let's go back to what we got for the max velocity somewhere. Max velocity, we got 0.47, so you do want to make sure that that's less than that, and in fact it is. So I think we're good. Alright, moving along, letter L says, what is the JKL acceleration at 3.3? So at 3.3, again, we're somewhere over here. So we're just going to use our F equals kx again, or negative kx, and set that equal to ma. So I think we did this before at the peak, but now we're a little bit less than the peak. So A equals negative kx over m. Okay, 19.7 negative. X was negative 0.088 divided by our mass of 2. Okay, plug that in, and I get an A of 0.867. Positive. Why is it positive? Well, look at your location. We're right here, and the force is pushing this way. So our acceleration is to the right. That's why we have a positive acceleration when we're at a negative displacement over here. All right, moving along. LM, sketch a VT graph. Actually, I'm going to do that right on here. So one of the things I want you to notice is that when displacement is at a maximum, velocity is at a minimum. So we're stopped here, and we're also stopped here. And when displacement's at 0, that's when our velocity is at a maximum. So notice we're going to start right here at 0, or 0 over here. Now as we move this way, we're moving in the negative direction. We're going to peak out at that 0 point right here, which represents that right here. And this is going to follow a similar kind of curve. So it's going to be something like this. And now we're going to start going up. We're going to slow down going this way. And then we're going to eventually stop right here. And we're just going to continue this. So it's going to look like this. It's going to be another curve. Now this would be a sine curve. The other one was cosine. And boom. So that's going to look like that. So that's our velocity. We could label the peaks here because we figured that out somewhere. Where was our Vmax? Our Vmax was 0.47. So yeah, if we constructed a whole nother graph, you'd want to label that right there as our 0.47, our peak. Okay, so that's what that graph would look like. What about the acceleration? So our acceleration graph, now acceleration, it almost follows exactly with A. So notice when we're right here, this is when it's it's at its maximum extension. So it's going to be pulling it this way, right, at max force. And then as it passes through here, it's going to be 0. So the displacement would be 0. And then same thing over here. And now it's going to be compressed fully, and therefore it'd be the full force or full acceleration. The difference though is over here we have a positive A, but the acceleration's to the left. So the signs are going to be flipped. So in other words, we're going to start down here at our max, at our minimum, or our most negative value, and we're just going to follow the same kind of cosine curve. I guess this would be a negative cosine curve. We're going to go up, so it's going to peak at that 1 second point, half a cycle, come down, and so it looks almost identical, it's just flipped, and down like that. So that would be our acceleration curve. So orange is velocity, green is going to be acceleration. Now what would the peak be here? We calculated that earlier. That was 1.48 meters per second squared. All right. Ooh, finally made it. Last question. How would displacement look if there was friction? Well, if there was friction, let's draw this right below. Essentially, it would look the same. It'd have the same exact period. Everything would be the same. The only difference would be, let's see, what color do we want? Purple. The only difference would be it would start to fade. The amplitude would get less and less over time. And that's because we're losing energy, so our US would get smaller and smaller over time. But the period would actually be the same. So it would have the same exact period, same exact frequency. The amplitude would just be decreasing over time. Okay? Changing into heat. All right, so I hope that was a good summary for you. See you later.